Assalamu alaikum. In this video, we are going to cover three subtopics of heart physiology. First one, we will look at the SA node, rhythmical discharge of SA nodal fiber compared to ventricular fiber, then cardiac cycle, all of its phases in the cardiac muscle, and the third one, ectopic pacemaker and the natural pacemaker of the heart. So now we start from here, a specialized excitatory and conductive system of the heart. The cardiac impulses are transmitted from SA node through AV node, internodal pathways to AV node, and then from here AV node to bundle to AV bundles from here to Purkinje fibers, right and left branches of the Purkinje fibers. Here is the graph depicting the electrical activity for the conduction of impulse in the sinus nodal fiber, and we will compare it with the ventricular muscle fiber electrical activity. In ventricular muscle fiber, the resting membrane potential is minus 85 millivolts, while in the sinus nodal fiber, the resting membrane potential varies from minus 55 to minus 60, that is less negative as compared to the ventricular muscle fiber. We will discuss its reason later. First, we consider the events in ventricular muscle fiber. At minus 85 millivolts, there occurs a threshold leading to the opening of the fast sodium channels, which will lead to influx of sodium ions into the cell, and action potential spike will occur. After this, here occurs a plateau phase in the ventricular muscle fiber, which occurs due to opening of slow sodium and calcium channels, which will lead to slow incoming of these ions into the cell fiber. After that, the action potential will decrease back to its resting level. In this phase, there occurs opening of the potassium channels, and the potassium ions will move outward out of the cell, and leading to drop of potential back to the resting level of minus 85 millivolts. Take it under consideration that there occurs a rapid spike of action potential, and again a rapid spike of return of action potential to the resting level. There are three membrane ion channels, both in cardiac muscle and skeletal muscle, which we have studied previously, and well informed of all these channels. First one is here fast sodium channel, slow sodium and calcium channels, and potassium channels. Electrical conduction in sinus nodal fibers. In SA nodal fiber, these fibers are naturally leaky to the sodium and calcium ions, which leads its resting potential minus 55 millivolts, that is less than that of the minus 85 millivolts of the ventricular muscle fiber. Here, the resting potential is less because of the natural leakiness of sodium and calcium ions from the slow sodium and calcium channels, which lead to the incoming of these positive ions into the cell, and the potential will become less negative. At minus 45 millivolts, there occurs threshold for the discharge of electric impulse. After that, there occurs the opening of slow sodium and calcium channels, which lead to its action potential. Here, understand the curves. Here it is the rapid upstroke of the action potential, and there is not rapid, there is a gradual rise in action potential, and again gradual drop of action potential back to its resting level. This is because of slow opening of the channels, and here occurs the rapid opening of the rapid ion transfusions. After returning of the action potential back to threshold, there occurs a hyperpolarization of the sinus nodal fiber cells. This hyperpolarization occurs as After opening of the potassium ions for return of action potential to the threshold, these potassium channels remains open for 1/10 of a second, and which leads to the additional removal of potassium ions, that is positive ions, out of the cell, and the cell potential will become more negative. This phase is referred as hyperpolarization. After hyperpolarization, again there occur the leakiness of sodium and calcium ions, which will lead back to the membrane threshold potential, and then again the cycle will be repeated. There arise two questions really. First one is, why does this leakiness to sodium and calcium ions not cause the nodal fibers to remain depolarized all the time? There are two reasons for this. Firstly, that the sodium calcium channels become inactivated after opening for the 150 millisecond, and the second one is here that the potassium channels open. Potassium channels open, and which will lead to the outflow of potassium ions out of the cell, and the membrane will become repolarized. Here it is that why this new state of hyperpolarization not remained forever. This state of hyperpolarization, which occurs due to additional outflow of potassium ions out of the cell. The reason for this is that during the next few tenth of a second after the action potential is over, progressively more and more potassium channels close. Inward leaking sodium and calcium ions once again overbalance the outward flux of potassium ions. Here occurs the leakiness of sodium and calcium ion, which will overbalance the outgoing of the potassium ions. The next topic that we are going to cover is the sinus node as a pacemaker of the heart. The impulse normally arises in the sinus node, but in some abnormal conditions, the other parts of the heart can also exhibit intrinsic rhythmical excitation, which are AV nodal fibers or Purkinje fibers. Okay, the reason for this is that the faster discharge rate of the sinus nodal fiber than that of the AV nodal and the Purkinje fibers. Let us have the comparison of the discharge rate of all these three fibers. AV nodal fibers have intrinsic rhythmical rate discharge of 40 to 60 times per minute. Purkinje fibers have 15 to 40 times per minute, and while that of the sinus nodal fibers have a rhythmical discharge of 70 to 80 times per minute. So why does the sinus node rather than the AV nodal Purkinje fibers control the heart's rhythmical activity? The answer, there are two main reasons for this. The first one is that the rhythmical discharge rate is faster for the SA node as compared to that of the AV nodal or Purkinje fibers. And the second one is that after first discharge, the sinus node discharges again before either the AV node or Purkinje fiber can reach their own threshold for self-excitation. Therefore, the new impulse from the sinus node discharges both the AV node and the Purkinje fiber before the self-excitation can occur in either of these. So this means that the sinus node overdrives these both AV nodal fibers and the Purkinje fibers, as its rate is faster than that of the AV nodal fibers and the Purkinje fibers. But under some abnormal conditions, the SA node will not act as a pacemaker. Some other parts of the heart develops a rhythmical discharge rate that is more rapid than that of the sinus node. Okay, so in this case, the abnormal pacemakers will be developed at AV node or AV nodal fibers or Purkinje fibers, and in rare conditions in the atrial or ventricular muscles. Here is the definition of ectopic pacemaker. A pacemaker elsewhere than the sinus node is called as ectopic pacemaker. This abnormal pacemaker causes abnormal sequence of contraction of different parts of the heart and leads to debility of heart pumping and decrease the cardiac output. The cause of the shift of pacemaker is that there is a blockage of transmission of cardiac impulse from sinus node to other parts of the heart. Mostly when AV block occurs, the impulse from SA node cannot be transmitted to AV node. Okay, the impulse conduction path from SA node from SA node to internodal pathways and then to the AV node. But when AV block occurs, from the impulse cannot be conducted from SA node to AV node due to blockage in these internodal pathways. When this AV block occurs, a new pacemaker will be developed in the Purkinje system of the ventricles. When this happens, the AV bundle block occurs, and the new pacemaker, that is Purkinje system, doesn't begin to emit its intrinsic rhythmical impulses until 5 to 20 seconds. The reason for this is that as the SA node was overdriving the Purkinje system, and the Purkinje fibers were in suppressed state. So after 5 to 20 seconds, Purkinje fibers will be able to emit any other impulse. So in this duration of 5 to 20 seconds, the blood supply to the brain of the person blocks and the person faints. This condition is known as Stokes-Adams syndrome. If the delay is too long, it can lead to the death. Now let us discuss the cardiac cycle. This cycle is mainly covers all the process or all the phases occurring while the heart undergo contraction. Okay, we will understand this cycle from this graph. We will try to correlate these respective pressure and volume curves to understand thoroughly the cardiac cycle. Here it is the ECG, electrocardiograph, ventricular volume graph, ventricular pressure curve, atrial pressure curve, and here it is the aortic pressure curve. So in cardiac muscle, there occurs first the electrical activity. Okay, that is that we will see it here in the ECG, this yellow curve graph, PQRST waves. And then after this electrical activity, there occurs the mechanical activity, which will lead to contraction or relaxation of the respective heart chambers. So firstly, we start from here. P wave, which refers to atrial depolarization. Okay, means after this atrial depolarization, the atria will undergo contraction. So here first here occurs P wave, then in this black curve here, which shows the atrial pressure, atria undergo contraction after this atrial depolarization. There occurs a rise in pressure curve as the atria contracts, and after the atria contraction, the AV valve closes. As the AV valve closes, in the atrial pressure curve, there occurs a small C wave. This C wave occurs because when the AV valve closes, there occurs backflow of blood from ventricles into the atria, and there occurs bulging of the AV valve, which lead to this C wave, formation of this C wave in the atrial pressure curve. Now in this ECG curve, we see this QRS wave, which refers to the ventricular depolarization. That is, after these waves, there occurs the ventricular contraction. So now, after the closure of AV valve, there occurs the rise in ventricular pressure, which is referred as the ventricular contraction. And as the ventricle completes its contraction, here at this point, when the pressure in the ventricle rises above 120 mmHg, the aortic valve opens at this point. After opening of this aortic valve, the blood will be ejected from ventricle into the aorta, and this phase up from this point to this point is referred as the rapid ejection phase of the ventricle, and then from here to here, this phase is referred as a slow ejection phase of the ventricle. After the ejection of blood here occurs at this aortic pressure curve, aortic valve closure. This aortic valve closure leads to a incisura, that is pressure changes, which occurs because the blood tends to backflow from aorta into the ventricle, and this pressure change occurs here in the aortic pressure curve. Now, after QRS, there occurs T wave, which represents the ventricular repolarization. That this means after this T wave, the ventricle will undergo relaxation. So here, after the closure of aortic valve, at this point, the ventricular pressure decreases, as indicated by this graph line. The ventricular pressure decreases. This phase is referred as isovolumic relaxation phase of the ventricles. After this isovolumic relaxation phase of ventricle, the AV valve opens and the blood from the atria will be transmitted into the ventricles. This line here shows the constant pressure, that is, pressure remains constant both in atria and the ventricle, as the atria is not contracting, and the blood, there occurs a passive flow of blood from atria into the ventricles, and the pressure of both remains constant here. Before the opening of AV valve in the atrial pressure curve, there occurs this small V wave. This wave occurs because of the venous return into the atria, which leads to a little rise in pressure and refers to as this V wave. Here, after this closure of aortic valve, the aortic pressure curve shows a decrease in pressure as the blood has been transmitted from aorta into the arteries and through arteries ultimately to the body tissues. This blue line here shows the ventricular volume curve. Here at A wave, as the atria was contracting and the blood was being transmitted from atria into ventricle, there occurs a rise in volume of the ventricle. And there occurs at this point isovolumic contraction in the ventricle. So here occurs no change in the ventricular volume, that is, ventricular volume remain constant. And then after that, in the ejection phase, rapid ejection phase and the slow ejection phase of the ventricle, there occurs a decrease in ventricular volume because as the blood has been ejected from ventricle into the aorta. And then after that, after the AV valve opens, there occurs the passage of blood from atria into ventricle, and there occurs rise in ventricular volume. So this cycle goes on further from here. The atrial contraction, then ventricular contraction, then ventricular ejection, ventricular relaxation, and then again the next cycle starts. That is the filling of this one is here filling phase of the ventricle, passive filling phase of the ventricle. And here is the P wave, atrial depolarization, QRS wave, ventricular depolarization, and T wave, ventricular repolarization. So these are the respective events which occur in the cardiac cycle. Here is the definition of cardiac cycle. The cardiac events that occur from beginning of one heartbeat to the beginning of the next are called as cardiac cycle. Here is a point, that is function of atria as a primer pump. Only 80% of the blood flows directly through the atria into the ventricles even before the atria contract. This point is represented by this line here, that after the AV valve opens, the atrial pressure and the ventricular pressure remains constant as there is no contraction of atria and ventricle. So after this, 20% filling of the ventricles occur by the atrial contraction. So atria act as a primer pump that increases the effectiveness of pumping by 20%.